This is section 14 of the C4 booklet, Integration by Parts. As usual, as you take notes, you may need to pause. I won't be pausing like I would be in a lesson to give you time to write things down. You'll have to take responsibility for that yourself. We're on page 26 of the booklet, Integration by Parts. So the integration by parts formula comes from the product rule. So product rule is y equals u times v, y dx equals v times du by dx plus u times dv by dx. So we're going to rearrange that and integrate it. So we have u dv by dx equals y by dx minus v times du by dx, by taking v du by dx from both sides. We then integrate both sides. We get the integral of u to v by dx equals the integral of y by dx minus the integral of v du by dx as we integrate term by term. Integrated y dx will simply just give us y. With everything else left unchanged, and to keep everything in terms of u's and v's, y is equal to uv, so we get the formula, the integral of u times the v by dx equals u times v minus the integral of v du by dx. And that's the integration by parts formula, and it is in the formula booklet. Now, whereas the integration by parts formula is always true, there are only certain cases where you end up with an integral on the right hand side that's easier to integrate from what you have on the left hand side. And in a sense, it's about choosing your u correctly in the cases where you're expected to use integration by parts. So the most common function will be x, but that should only be your second choice where it exists. So the second best is x, but that is the most common choice. The one that outranks absolutely everything is ln x. And that goes first. So you see ln x, that's your u in an integration by parts. At this level, at least, if you go up to higher levels, you may also find there are other functions that exist on the ln x line. For 3, it's powers of x, so x squared, x cubed, so on. You would be unlikely to see anything higher than x squared on a C4 exam. And number 4 is pretty much anything else you might see, so e to the x, sine x, cos x. So remember which order you should be picking your u's. ln x trumps everything. X is probably the most common thing that you will use. In many cases you do an x squared. We'll deal with a case 4 here, but it, as yet has never turned up on an exam. So first example, we've got x times cos x dx. No ln x, but our x is there, so u is equal to x. Leaving dv by dx to be cos x. Differentiate the u to get du by dx. And we get 1. Integrate the dv by dx to get v. The integral of cos x is sine x. We then apply the formula. I say it's in the formula booklet, so you will not need to remember it. So inputting it, left hand side is integral of x cos x dx, right hand side u times v is x times sine x, minus the integral of v times du by dx, so sine x times 1. And as you can see, integrated sine x is easier than integrating x cos x, so the right hand side is easier to do than the left hand side. So we carry on the right hand side. The integral of sine x is minus cos, so we end up with plus cos x plus c. that's a fairly standard integration by parts example. Example 2, we have an ln x, so that trumps everything for our choice of u. So dv by dx is equal to x squared. Differentiate the u. Du by dx equals 1 over x. Integrate the dv by dx. V equals x cubed over 3. And then we apply the formula. The integral of u dv by dx equals u times v minus the integral of v times du by dx. Input our values. Integral of x squared ln x dx equals u times v x cubed over 3 times ln x minus the integral of v times du by dx, so 1 over x times x cubed over 3, and one of the x's will cancel, so we get x squared over 3 dx. And again, the right hand side is easier to integrate than the left hand side. So you get x cubed over 3 ln x, integrate x squared over 3, increase power by 1, divide by the new power, minus x cubed, divide by 3, turns that to a ninth, plus c. And that's example 2. Example 3 is a kind of special case. It's one of the only occasions where there's only one function and not an explicit product of two things. So again, ln x features. So u equals ln x. V by dx, well there's no other explicit function to multiply, but ln x times 1 is ln x. So v by dx is equal to 1. Differentiate u, du by dx equals 1 over x. Integrate the v by dx. V is equal to x. Apply the formula, copying it down from the formula booklet. So u times v is x times ln x minus the integral of v times du by dx. So x times 1 over x, the x's cancel and we just get 1. And the integral of 1 is simply x, so we get x ln x minus x plus c. So that's a special case that you should learn and know. 2 more examples. Example 4, we've got x squared e to the x, so we haven't got a single x, we haven't got ln x. So u is our power of x, so x squared to v by dx is e to the x. Differentiate the u, du by dx equals 2x. Integrate the v by dx, well e to the x integrates to itself, so we get e to the x. Apply the formula. From the formula booklet, we're going to get the integral of x squared e to the x dx equals u times v, x squared times e to the x, minus the integral of v times du by dx gives us 2x e to the x. Now, we can't integrate 2x e to the x, but it is simpler than x squared e to the x. And what we can do is we can repeat the integration by parts to basically give us, to integrate that part of it, which we can add to that. So in a sense, we're going to do an aside over here. So in this case, the u is 2x, the 2 can go either side. The v by dx is e to the x. Differentiate u du by dx is equal to 2, integrate into v by dx, v equals e to the x, apply the formula from the formula booklet. So we get the integral of 2x e to the x dx equals u times v, so 2x times e to the x, minus v times du dx, 2 times e to the x. We can integrate 2e to the x, so we end up, when we put it all together, with a full integration. So 2e to the x integrates to itself, so we get 2x e to the x minus 2e to the x. I'm not going to bother with the integrational constant here, since I can just add it in at the very end of my working. So sticking it in, x squared e to the x minus, open bracket, 2x e to the x minus 2e to the x, plus c, multiply out the bracket, x squared e to the x minus 2x e to the x, minus times the minus is plus 2e to the x, plus c. That is our final answer. So basically x squared would involve using integration by parts twice, x cubed 3 times, and so on. Because it's just reheated processes, you tend not to see anything higher than x squared on C4. There is a methodical way of doing higher powers without doing the individual steps. It's a process called reduction formulae, which you would see in the further pure modules. Final example, bit of unusual, not really been in the exam, never been in the exam so far, but interesting to see, and a little bit unusual. When you've integrated, you'll feel like you haven't integrated this at all. So part A, part B is just doing the limits once you're done. It's just to show that if you've got limits in integration by parts, you can just do the whole process normally and then just deal with the limits right at the end. So we've got e to the x cos x. So it doesn't actually matter, and according to our order, e to the x or cos x doesn't matter which. So it's easier to differentiate a trig than integrate trig for some people, and e to the x is easy to integrate or differentiate. But in a real sense, it doesn't matter which way round you do this, you'll get the same result. So differentiate cos x, you get minus sin x. Integrate e to the x, you get e to the x. Apply the formula. Again, taken from the formula booklet, we get the integral of v to the x cos x dx equals u times v e to the x cos x minus, but we've got minus here, so we can take that to the front and make it a plus, e to the x sin x dx. So if you look at this, on the surface it looks the same level of complexity, and it is really. So e to the x cos x is e to the x sin x, just equally difficult to integrate. Well, we'll do by parts again with the e to the sin x. So u equals sin x, to v by the x equals e to the x. Differentiate the u, du by dx equals cos x. Integrate the e to the x, v equals e to the x. Apply the formula. Again, taken from the formula booklet, so no need to remember it. The integral of e to the x sin x dx equals u times v e to the x sin x minus the integral of e to the x cos x dx. Sub that into here, we get e to the x cos x dx equals e to the x cos x plus e to the x sin x minus the integral of e to the x cos x. Now what's unusual is we've got the same integral now on both sides. So we can add that integral to both sides and we'll get two lots of the integral of e to the x cos x dx equals e to the x cos x plus e to the x sin x. Then to get the integral we just need to divide through by 2. So we get e to the x cos x plus e to the x sin x all over 2. And oh, we've kind of integrated without integrating, so we still need our plus c constant of integration. So it's a bit unusual, and it hasn't turned up in an exam so far, but if it did, that's how you deal with it. Part B, just applying the limits. So it's the integral of e to the x cos x, so the integrated form is e to the x cos x plus e to the x sin x all over 2, limits of ln 2 and 0, stick them in and subtract. So e to the ln 2 cos ln 2 plus e to the ln 2 sin ln 2 all over 2. Take away e to the 0 cos of 0 plus e to the 0 sin of 0 all over 2 and calculate. And this is so complex you probably would be asked for a decimal if you're ever asked to do this at all. May note of course that e to the ln 2 is just 2, so that simplifies those parts. Remember this is integration, so your angles need to be in radians. Minus e to 0 is just 1, cos of 0 is 1, sin of 0 is 0, so that term does simplify to a half, even though this term does not simplify nicely at all. So 3 significant figures, 0.908. And nicer numbers you may be asked to give an exact answer, like we have done in other sections. And that concludes this section.